Okay, so I'd like to start by thanking the organisers of the conference for inviting me to present this work. This work is a combination of works that I've been developing in the actuarial and statistics community over the last few years, and it relates to stochastic models for mortality and how those mortality models can then be used to infer things about population demography and actuarial and insurance and longevity modelling for life aspects of insurance. So today my talk will be about statistical properties of mortality data at a national level statistics setting. And I'll start with a motivation for why this type of modeling is important. And then I'll show you some interesting stylized features, statistical features that I've extracted from data of national level statistics of mortality. And we'll talk about what that means for modeling purposes briefly at the end, because it's a short talk. Okay, so my name is Gareth, Professor Gareth Peters. I'm from Heriot-Watt University in Edinburgh, and I've been working on actuarial problems, statistics and actuarial problems for a number of years. So this is a portion of the kind of work that I do related to perspectives on mortality modelling. Okay, so the modelling and management of systemic mortality risks are two of the main concerns of large life insurers and pension plans. I put this sort of summary here because not everyone in the audience will be familiar with actuarial models and the importance of these aspects to actuarial modelling. So I'll give a little bit of a motivation more than I would if I was talking to an actuarial community. So modelling, what is the best way to forecast? I have these questions. What is the best way to forecast future mortality rates and to model the uncertainty surrounding these forecasts? That's the question we'll be focused on today. But other important questions that they often look to address are also, how do we value risky future cash flows that depend on future mortality rates? So this is the two main modelling questions, if I had to summarise them in brief, that relate to actuarial modelling for mortality. And then there's a management set of questions. Management, how can this risk be actively managed and reduced as part of an overall strategy of efficient risk management? And what hedging instruments are easier to price than others when it comes to longevity and mortality contexts and pensions and insurance and life insurance context. Okay, so this is the modelling and the management type of questions, and we're going to focus on what is the best way to forecast future mortality rates and to model the uncertainty surrounding these forecasts. So I'm going to give some context of mortality modelling and population demographics. So start off with this plot here. These plots go due to a really interesting group called Our World in Data that allow us to use these types of summary data that they have for research exercise, and they have some nice demographic data sets that we can visualize and use. So I'm going to use this to make a point that this is time on the y-axis in years since 1950 through to 2100, so that's a projection, and annual population growth in percentage on the y-axis, so that's in percentage terms. So what we see in red is our evolution of the world's population. This is a global annual world population growth rate, the growth rate since 1950 to 2100, so the projection as of I think it was around about 2015, when this was last revised. And so what we see is that over history, we've seen this growth in population percentage. The growth rate has been going up in the population until around the mid-1960s, where we had a peak, 1962, at 2.2% growth rate. And then since then, the population growth rate has been in steady decline, quite rapid decline. And we see that now the population growth rate is approaching 1% per year. And if we do continue on this extrapolation of this growth rate over time, if something doesn't change, and given the aging population structures we have in most developed economies, this is likely to happen. By 2020, the world population will be approximately 7.8 billion people, and the projected world population by 2050 will be 9.7 billion and 10.9 billion by 2100. So that in itself is not necessarily a problem. The challenge that we'll face is the age brackets that are largely make up that population and where the concentration of the majority of individuals will lie in those age brackets. If we stratify age by blocks, like 5 to 10 year blocks, where do most of the population live within those age brackets? Because obviously that will have consequences for requirements for funding for hospitals, for medicine, for pensions, etc. So it's very important to understand this context. So this is the global level. If we look by country, this tells us an interesting picture. So this is the world population by level of fertility over time from 1950 to 2010, similar time period. And what we see is the red curve here. So on the y-axis, we have cumulative share of the world's population in percentage. And we have red, orange, and blue lines, the red line being the 1950 to 55 global average fertility rate, which was 4.97. And that was decomposed in percentage terms according to the following breakdown by country. So we see that the length of each line corresponds to what proportion of the global fertility level was attributed to a given country. And so here on the right, we see the number of children per woman, total fertility rate. And so in China, for instance, back in 1950, the number of children per woman was greater than 6. In India, it was greater than 5, close to 6. And in US, it was at that time around about 3. In Australia, it was around about 3. Japan, it was even around about 3. And I think it was only in smaller countries in Europe, such as Luxembourg, that the fertility rate, number of children per woman in 1950 was around about 2. Now, what we've seen is a steady decline in the number of children that families are having, that women are having. And we've seen that the rates, therefore, as we see the proportion of countries that fall below 3 children per household, per woman, is actually increasing significantly. So we see that the share of populations that have less than 3 women, less than 3 children per woman, have drastically increased, and therefore this blue line, which represents 2005 to 2010, rapidly decreases at the front and then flattens out at the bottom. And the consequence of that, the way we interpret that, is that more countries, especially countries with large populations, countries that make up more than 60% of the global population, like India, China, US, Brazil, Indonesia, countries that have fallen below this level of 3 children per woman. And it's only in a few countries like Nigeria, Yemen, Saudi Arabia that we're still exceeding those 3 children per woman. So the consequence of this is quite pronounced, because this dashed line here, this is the global replacement fertility level. So what this means, this is around about 2.3 in 2015. So what this means is that the total fertility rate at which the population size stays constant. So if enough countries fall below this global replenishment level, it means that we will no longer have an increasing population, we'll have a decreasing population, which again, in itself is not necessarily a major consequence if it's only short-lived, but it could be quite substantial if that decrease in population also corresponds to significantly aging populations in the groups for which this decline occurred. And this is the concern, right? And so we can also see this when we look at population pyramids. So here I've shown age distribution of the world population by sex. And so we have on the left-hand side the age distribution for men, and on the right-hand side we have the age distribution for women. We have on the y-axis the 10, 20, 30, 40, so it's deciles of your age up to 90 years of age. And we have on the y-axis, starting from the middle, going left, going towards the left, towards the negative numbers, we have the years, 1950, 1960, 1970, 1980, through to 2050. And these are the population pyramids. So what we see is that in 1950, globally, the majority of the population was made up with people between 0 and 30 years of age. So really in a productive working age demographic, in terms of periods of time when health is not affecting your working conditions, and when you're still in a learning phase, when you're still in a production phase. And so this is very good for economies, because you'll get this demographic boost in productivity, because you have a lot of labor force to do a lot of different jobs. And so as we've seen from 1950, as we push through 1960, 1970, 1980, 1990, 2018, we've seen a widening out of this demographic triangles for both male and female. It's not symmetric. There is an asymmetry here, but it's not too badly asymmetric, at least in 1950 through to 2018. But what we see is that as this widens out, it gets more rapidly more rapidly wider. And the consequence of that is that there's more and more people surviving longer and longer into older age groups. And so we need to account for that when we take into consideration budgets for hospital, for pensions, and for aged care facilities, for instance, resources for those. And so what we see is that by 2100, we'll have this very globally, this is globally, we'll have this very wide population triangle where it's almost uniform in the number of people who are 80 years will almost be the same as the number of people who are 70 years old, will almost be the same as the number of people who are 60 years, etc. And that's never been the case in the recorded history that we have here. So this is a very unusual demographic profile compared to what we've experienced up until this date. So we'll need to make policy changes to accommodate that and ensure that we have enough pension to cover those changes. Okay, so what about life expectancies? Life expectancy, so two components, life expectancy, the average number of years that an individual is expected to live based on current mortality rates. Healthy life expectancy is the average number of years that an individual is expected to live in a state of self-assessed good or very good health. So note, expectations of life are often calculated in one of two ways, the period life expectancy and the cohort life expectancy. Cohort life expectancies are calculated using age-specific mortality rates, which allow for known or projected changes in mortality in later years. So we have a plot here of life expectancy from 1941, and we see that most countries, apart from, say, Australia and a couple of European countries, and perhaps North America, are having life expectancies in 1941, which were already exceeding 55, 60, 65, 70 years of age. But majority of the world's population had life expectancies not much more than 20 to 30 to 40 years of age. And so that was obviously due to all kinds of factors to do with disease and education levels and famine, etc. So as the world has progressed, if we look at the 2015 profile by country, we see that most countries, we see people are living longer. It's not universally the case, but in majority of countries, we see that life expectancies have increased. And in Australia, they're now exceeding 80. And in most other countries, developed countries and developing countries, they're at least exceeding 55, if not 65, 70. And that's partly due to increased living conditions, partly due to increase in education levels, partly due to increase in medical breakthroughs and immunization schemes, for instance. Okay, so if I look at the UK, we get some stylized facts. This is just for England and Wales, 1700 to 2013. We see that there's some stylized facts to do with life expectancy. So this is life expectancy, cohort life expectancy for 70-year-old, 60-year-old, 50-year-old, 40-year-old, 30-year-old, etc., through to life expectancy at birth. And we see that there's different rates of growth in these cohort life expectancies and different volatility and shocks that have occurred over time. So I'll probably skip over this one. This one's not so important. This is just pointing out the fact that although people are living longer, the amount of years that they're living longer in healthy state is declining. So in other words, people are living longer, but they're living in a debilitated or poor health state for more years of their life. And so this has all kinds of consequences to do with medical costs, medical insurance, and also productivity in the workforce. So the percentage of life in poor health at birth is 20% to 22%, and at age 65 for males is 43% and 46% for females. So quite a lot of lived years. This is number of years in poor health is 8 years for males at 65. This is in 2013, and 9 years for females in 2013 to 2015. But this is actually increasing as well. So aging populations are a major challenge for many countries. Fertility rates are declining while life expectancy is increasing. Longevity risk, the adverse financial outcome of people living longer than expected, possibly of outliving their retirement savings. We have to study this longevity risk. It's a long-term demographic risk. It has significant implications for societies, and it manifests as a systemic risk for pension plans and annuity providers. Policymakers rely on mortality projection to determine appropriate pension benefits and regulations regarding retirement that should take into account this systemic risk in the population. So now, how do we build such models to accommodate this? So we're going to talk briefly about stochastic mortality models. So there's a range of different types of classes of stochastic mortality model. They're very diverse, so we have to categorize them, and this is one way to categorize them. Single age group models. So these seek to model the individual mortality evolution, either the force of mortality or the annual death counts. And in the works that I'll talk about, or you can see in the references in this talk, there's a combination of both the death count models for single age group as well as the force of mortality models. Typically, such models include temporal smoothing splines, which called in this literature, it's called a graduation effect. Demographic factors can be count processes or functional regressions, or they could be ARIMA-SARIMA type structures. And then you have, from the single age group, you move into a different category, which is the term structure of mortality, where you model multiple age groups. And so typically model the log mortality rate across the term structure of mortality. Typically such models include temporal smoothing splines, period effects, cohort effects. And nowadays there's a third category of models which is starting to arrive, which is multi-population models, where you model different countries jointly together in their demographic experience. And we have a couple of papers on that as well. Okay, so evidence for additional structure in time series regression models for mortality projection. So the main bulk of this talk is then to show that a lot of these models are missing some key stochastic attributes that you should incorporate if you want to get better predictions or better forecast of your mortality rates, so that you can then improve on your risk assessment for longevity and mortality prediction, like life table construction, for instance. So this is related to the fact that many national level statistics for mortality demonstrate long memory properties. So I'm going to show that in this rest of this talk. So I won't have time to talk in detail about the mathematics of the long memory. You can see that in the papers that are now published in Aston Bulletin and Annals of Actuarial Science. But I'll skip over, I'll briefly mention this, and then I'll show you the results to finish off this talk. So normally this is a 1 hour talk, so I'm giving it in a shorter time. So what is a long memory feature? Long memory basically refers to the level of statistical dependence between 2 points in a time series. So given a stationary time series process, let's say y, this is our time series, and it will take values in the integer, in the natural numbers, including 0. Behrend defined conditions for long memory stationary process via divergence of the autocorrelation function, the ACF. So in other words, if I calculate the autocorrelations as given by this formula here, covariance between the lags scaled appropriately, and I sum up the absolute value of those correlations, and I take the limit of the sums of these values to infinity, will that be divergence or will it be convergent series? So if it's divergent, we say that there is a long memory or persistence property, because very distant lags are still related to the current value that you're observing, because that correlation doesn't decay fast enough for this sum to converge. So if this is divergent, we say there is a persistent long memory present, but there's different types of long memory, and we'll talk about particular ways to characterize that. So since the early work of Hurst in 1951, long memory phenomena has been recognized in diverse fields of application. And so people characterize these. So to understand long memory, we need to think about backshift and difference operators in time series. This is one way to understand it. To obtain temporal integration of a time series. So consider a time series YT. The backshift operator and difference operator are given by B of YT, which gives you YT minus 1, and 1 minus B, this is the difference operator of YT, gives you YT minus 1. Okay, so it's a finite difference. Typically, one considers an integrated, an ARIMA model, ID model of a differencing operator 1 minus B to the D for integers D in the natural numbers, which is used to differentiate, in inverted commas, temporal trends for the time series to make it weakly stationary. This is the classical linear process theory. Right? So in a long memory model, one replaces the integer difference operators with a fractional difference operator. So now the D that we're familiar with for integer differencing for ID processes, we're going to replace with D being a fraction between 0 and 1/2. Now, you can generalize this, but the focus we have here is just on D between 0 and 1/2. And this extends the fractional difference to the difference operator to a fractional difference operator. And you can represent this in different ways. So the fractional difference operator has a generator expressed in integer powers of the backshift operator B. So we can write it as 1 minus B to the minus D, which would be the inversion of that difference operator on the autoregressive, on the white noise sequencing and ARIMA model to get the Wold representation. It will be written as an infinite sum of weightings, which are weighted by the gamma function. This is coming from the fractional difference definition, in monomial powers of b, so b to the j, where j is an integer, an infinite sum of those from j equals 0 to infinity of weighted values of b to the j, where the weights are gamma functions of j plus d, which has a lag decay much slower than exponential, with rate depending on the fractional difference level, d between 0 and 0.5. So this leads us to what's called a Freema models. A Freema 0D0 model describes a long memory stationary process with a hyperbolic decay as opposed to a geometric decay of the ACF as compared to a standard ARIMA model, which would have geometric decay typically. So oscillatory autocovariance can also be captured. So this is a generalized form of this operator where we write the difference operator as 1 minus 2 ub plus b squared to the minus d, where d again is a fraction between 0 and 0.5. And then we can rewrite this as an infinite, as we can rewrite the generator of this fractional difference operator, this Gegenbauer form, with an infinite sum of Gegenbauer polynomial weights of b to the j, where the Gegenbauer orthogonal polynomial is written as this functional form here, where this square bracket is the integer component. We just round this to the integer, j over 2, and we have minus 1 to the q, 2u to the j minus 2q, gamma of d minus q to the j over this ratio. And the q is obviously the index of the sum. The u is another component here which dictates the oscillatory nature of this fractional difference. The Freema model is not an oscillatory ACF, and this fractional difference, the Gegenbauer form, gives you an oscillatory ACF, and you get this extra degree of freedom for u compared to d. So this fractional parameter d captures the persistence for a given long memory model. So now this relates to fractional Brownian motion, and I'll just quickly characterize that. So weak convergence of fractional time series to fractional Brownian motion. We can define a fractional difference characterizing process, qt, which is just 1 minus b to the minus d, where d is absolute value less than 0.5, and it multiplies a white noise sequence of normal 0, 1, IID. So we can define this process, qt. Then qt is a stationary and weakly dependent process because of this fractional differencing. Now consider the following scaled partial sums constructed from this process. We're going to call these sums zt psi, and we're going to sum the qt's over t psi summands and scale it by sigma t, where sigma t is given by this second moment of the sum of qt. The integer part is a number of terms. So this will be dictated by the proportion of time steps that we include. And so this will be a functional valued process. And we want to look at the convergence of this functional to a functional central limit theorem convergence. So we can make, Davidson proved in 2000, the following weak convergence holds for all d in absolute value less than 0.5 and all fractions of time between 0 and 0.5. zt to the psi converges weakly or in distribution to a scaled version of fractional Brownian motion, where the fractional Brownian motion is denoted by wd psi as t goes to infinity. And the scaling that you need to get this convergence to occur is given by this vd scale constant. I won't talk too much about this here. And the wd psi is a standard fractional Brownian motion, which can be rewritten in this standard fractional Brownian motion form as an integral against Brownian motion, a stochastic integral against Brownian motion with a kernel which has got this hyperbolic decay, psi minus s to the d minus s to the d, as between minus infinity and 0, and a second integral between 0 and psi of psi minus s to the d, and again an integral of Brownian motion, all scaled by a gamma function to get the scaling present. So this is just a standard representation of fractional Brownian motion. So we see this functional central limit theorem convergence of this scaled sum from our fractional difference. Why is that meaningful? Because it tells us that there's a direct relationship between the fractional difference power in our Gegenbauer or our Freema model and the Hurst exponent that comes in our fractional Brownian motion. And this relationship is linear. It's just d equals h minus 0.5. So that means if we have robust estimators for h, we can also then construct estimators for d. And that's really the observation that's important here. So next, what we do is we show that the estimators for the Hurst exponent can be used on mortality data. We take the rescaled range analysis model, the detrended fluctuation model, and the periodogram regression methods to estimate the Hurst exponent from our national level statistics. I won't spend time talking through those estimators, but they're present in our paper in detail. So I'll skip over that part of the talk. This is where they're constructed here. They're just using asymptotics of these sums, and we'll go to the results just to finalize. What we're showing here is a selection of countries from the Human Mortality Database: Australia, Belgium, Canada, Denmark, Finland, France, Iceland, Italy, Spain, Switzerland, Great Britain, US, and Japan, for instance. And the red here is female, and the blue here is male. And what we have, that's the x-axis by country, and the y-axis is by age groups, stratified by 5-year brackets. And what we have is the point estimators of the Hurst exponent. So I haven't converted it into D, the fractional power, but since there's a relationship of D of H minus a half gets me D, it's obvious. So what we have here is a Hurst exponent, and numbers for H which are greater than a half tell us that there is persistence or long memory structure in our mortality data at a national level. This is annual mortality data at a national level by gender and by age. So for most countries and for most age groups, we have persistence in the time series. And most mortality models are not accounting for this persistence. And our argument, and what we did in the models that we subsequently built, is demonstrate that we can significantly enhance mortality projection and life table construction by incorporating this persistence feature. Now, I won't have time to talk in detail about that, but you can read our papers to find the detail of that, or contact me if you're interested in more discussion. And so there we just did this. We did this by age and country. We also break this down by age group and estimated H for the entire, for all the countries put together. And so we see male and female again in pink and blue. And we see the median for all age groups was clearly above 0.5, which is at the bottom here, this bottom row here. It was much more between 0.8 and 0.85. So not only is there persistence, but the persistence is pronounced. It's quite strong persistence. And in addition to that, it also varies by gender quite significantly in age groups 15 to 65. So males have less persistence in the mortality experience than females. And here it's very, very significantly different across all the countries that were studied. And in addition, it changes over the age groups. And we can see that changing through time over the age groups. Some countries are exceptions, like Japan and Iceland and Spain in certain age groups, but majority of the analysis shows that there is strong persistence in all of these age groups. And the rest of this talk really, I just very quickly skim through, and I'll provide you the slides so you can read this in more detail. The rest of this talk just shows how you can then use that idea to build a family of GLAMA models. These are generalized linear Gegenbauer autoregressive moving average models. These are time series regression models. They're generalized because we have count distribution. We have a discrete distribution which we use a generalized Poisson or a double Poisson because it allows for overdispersion and underdispersion effects. And we also have a stochastic intensity. And the stochastic intensity is a time series model written here in equation 2, which has a Gegenbauer fractional difference on a characteristic polynomial for an autoregression with a log link to the force of mortality, mu xt, where x is the age group and t is the year, centered by some constant c, and then a moving average component with a characteristic polynomial for the moving average theta b, and a white noise sequence epsilon, which is usually white noise like normal 0, 1 or normal 0 sigma squared. So we calibrate variations of this model in quite sophisticated way using Bayesian methods and show that this enhances forecasting. So I'm just about to finish my time. So the distribution we chose for the counts was Poisson, generalized Poisson. Here's the functional form of our generalized Poisson. And we showed that this was far better than just simple Poisson binomial or negative binomial, and also includes those submodels anyway, and this was optimal. And we defined different families of model. We defined the MEL-CC, multivariate extended Lee-Carter cohort model. So this is a GLAMA model that incorporates into the the Gegenbauer ARIMA, the Gegenbauer autoregressive moving average force of mortality structure, both a stochastic trend with a period effect. The kappa t is a period effect, and the psi t is a cohort effect. And this is the state space representation of the period effect and the cohort effect. And we have 3 papers on that discussing how to do that and how to calibrate that. And then we also built what we call an LM-LM model, which is a long memory model. And then we replaced the period effect and the cohort effect with long memory components. So we replaced the period effect with a stochastic model for the long memory, and we incorporate into the cohort effect a fractional difference on the error. And we show that this model is outperforming all the other standard classical mortality projection models. And that's all I'll say. The rest of it is we provide some examples. Here's a very brief summary of the examples. This is by age group. This is an out of sample forecast from our MEL-CC model and our LM-LM model. The black line is the true observed sample that was left out of the calibration, and the red and the purple lines are the forecasts. The LM-LM is clearly the red one, and the purple one is the MEL-CC. This is the extended Lee-Carter model with cohort effect and long memory. And we see that this long memory model is significantly better at forecasting the mortality and therefore in constructing the life tables for most age groups, and especially important for age groups like 60, 55, 60, 65 retirement age and afterwards. We get far better forecasts than classical models. And this is true for female, and it's also true for male population, which I won't show you here. So I think that I'll finish there. I had a couple of slides talking about the importance of this, and I'll just say my conclusions to wrap up. So my conclusions from this sort of brief talk, you can read more details of this analysis in my papers, is that an aging population is a major challenge for many countries in the world, arising from declining fertility rate and increasing life expectancy. The adverse outcome of people living longer than expected, exacerbated by the record low interest rate environments, has significant implications for societies and manifests as a systemic risk for the governments and industry providers of retirement income products. At the same time, the long-term effects of defined contribution pension system that replace the defined benefit system need to be better understood. And retirees are faced with making many complex decisions under large uncertainties of lifetime and financial returns, accounting for government-provided means-tested age pension and possibly policy changes and preferences for consumption, housing and bequest. Furthermore, the cost of health and aged care are increasing significantly, making it very difficult for people and governments to plan and budget these costs due to significant uncertainty in predicting their future trends. So all of these problems have one common important component that relates to all of them, the ability to forecast mortality rates and construct life tables accurately. And that's really what the focus has been on the statistical part of this talk. So papers that you can look at for more details, I just put them on the screen here that you can find them on my webpage. We had a paper in 2017, a unified approach to mortality modeling using state-space framework. In 2018, we had a cohort effects in mortality modeling paper in Annals of Actuarial Science. These were both in Annals of Actuarial Science. In 2018, we did a paper on stochastic period and cohort effects state-space mortality models, incorporating demographic factors via probabilistic robust principal components. That was in risks. That was a multi-population, multi-country population study. We did a paper in Aston Bulletin on multivariate long memory cohort mortality models in 2019. And in 2020, we've had a few papers. Mortality models incorporating long memory improves life table estimation, a comprehensive analysis that was just accepted in Annals of Actuarial Science. And so 2020, we have evidence for persistence and long memory features in mortality data that's currently in almost finished review, second round of review in Annals of Actuarial Science, should be accepted soon. So hopefully you'll find those papers interesting. And if you have questions, feel free to reach out to me and discuss more details with me going forward. I'm always open to collaborations on these topics, and I welcome your chance to talk to me. It's difficult when we're not in person to talk together. Nice. Thank you again for the invitation to give this presentation, and I thank the organisers at Mahidol, and I hope that the conference goes well. Pleasure to join virtually. Thank you.